head injuries and oxidative stress. We're going to talk about later, there's a theory that, okay, when you're treating somebody with L-DOPA, you're actually hastening, everybody knows the word hastening? Quickening the progress of the disease, progression of the disease. And that's because you're going to be able to form free radicals when you metabolize dopamine, and we'll talk about that a little later on, that if you get excessive dopamine up there, you may generate these free radicals. I already told you about free radical damage, right? Rubber band, put a rubber band in the sun. Did I tell you that? If you ever want to see free radical damage at work, take that rubber band, put it in sunlight for a couple hours, and then stretch the rubber band. It snaps. Okay? And that's due to free radical damage. Well, free radicals destroy, okay, DNA, okay, and they cross-link membranes, making them very stiff and able to break open. But free radical damage, okay, is very, it messes up DNA, it causes mutations in DNA, it cross-links your cell membranes, and causes all type of problems. And we're going to come to that a little later on. Okay, the diagnosis is completely, actually it's almost the whole page is for your information, but the diagnosis, okay, how they diagnose it is described there, and then how they stage it, okay. Note that stage 5, you're restricted to a wheelchair or bed unless aided. So, don't have to worry about that. What we do have to worry about is we're going to go before those pages. I want to discuss, okay, just going to get this page up. I think it's just not working today. There we go. Okay, I'm going to go over the theory of this. Okay? Basically, various areas of the cortex can make the command for you to make a movement. But before you make that movement, you go and there is a place that sort of fine-tunes that movement. There are 2 places in the body that fine-tune movement. You should know one of them already. What would be one area that fine-tunes movement? Cerebellum. Okay? But there's another area. The other area is what we call the basal ganglia. And I'll explain what the basal ganglia is. But these basal ganglia, what they do is provide the involuntary part of voluntary movement. What do I mean by that? Remember I was talking about those automatisms, those things you do automatically? Okay, when the brain makes the command, you can make a crude movement. But what you need to do is, there's involuntary things you don't even have to think about, that you just do naturally. Like your arm swing, okay? Well, this area, this basal ganglia, what it does is it fine-tunes movement. Okay? So what happens is, these areas here of the cortex, okay, make the command for the movement. And what they're sent to is something called the caudate putamen. Nobody calls it the caudate putamen unless you're going to get really technical. Everybody calls it the striatum. It is 2 different structures stuck together. But the type of neurons in there, the tissue in there, is identical in both of these areas. But it's called the striatum. From the striatum, you go to something called the pallidum. Everybody says the globus pallidus. Everybody calls it the pallidum. Okay? Then, the pallidum can send it to subthalamic nucleus, but it doesn't have to. Then it goes to the thalamus. Okay? Particular areas of the thalamus, you don't have to know, ventral anterior and ventral lateral. And then it goes back up to the motor cortex, and then the motor cortex sends it with the command down the spine to the skeletal muscles. So once again, your cortex, okay, different areas of the cortex can command the movement, but before you actually make the movement, it goes to the basal ganglia to be, like I said, fine-tuned. Then the information is eventually sent to the thalamus, and then the thalamus sends it back to the motor cortex, and then the motor cortex goes to the spinal cord, sends the thing out to the spinal cord, and finally to the muscles themselves. Okay?
Question from my mom.
Yes?
So is the basal ganglia considered the caudate, putamen, and
Substantia, big three are substantia nigra, the striatum, which we already called it, and then globus pallidus, which is called the pallidum. So one, you got it basically, substantia nigra, caudate putamen, which everybody calls the striatum, and then globus pallidus, which everybody calls the pallidum. We're going to be talking about these in a few minutes. Okay? Now let's go to a simple discussion of the wiring of this whole thing. But before we do that, oh, don't tell me it. Wait a minute. Okay. They say that the basal ganglia, okay, is an area of inhibition and disinhibition. Okay? That's what sort of rules the entire area. Inhibition and disinhibition. Now, what was I saying? Okay. Oh, assume all neurons are spontaneously active unless they're inhibited by something. And the thing that inhibits them is GABA. So all neurons are considered to be spontaneously active unless they're inhibited by GABA or something else. Now, if you look over in the thalamus, we have glutamate neurons. Okay? We have glutamate neurons. Glutamate is the #1 excitatory neurotransmitter in the brain. Glutamate. Okay? GABA is the #1 inhibitory neurotransmitter in the brain. GABA. Now, here's all you really have to understand. Okay? The more impulses that the thalamus sends to the cortex, okay, the more movement you get. Notice that what you're sending is a glutamate projection, so you're going to excite the cortex. So the thalamus sends impulses to the cortex, and then you get the movement, like we said before. Actually goes to the motor cortex. So the more impulses you go, the more movement you're going to get. Now we've got to talk about inhibition and disinhibition. All right. The end is always going to be an excitatory neuron. This excitatory neuron is glutamate. And what you're going to try to determine, which I'm going to draw it the other way. Okay? What you need to determine, okay, is whether or not the glutamate neuron fires. Because if it does fire, we're going to get more movement. Now, if I activate this glutamate neuron, what happens? More movement. Okay? Now, I'm going to inhibit the glutamate neuron. So let's try this. Let's put a GABA neuron there. If this GABAergic neuron fires, what happens to the glutamate neuron? Doesn't fire, so you don't get movement. Now, take GABA, take the Flintstones. GABA, GABA, glue. Let's forget about this for now. Let's call this glue. Okay, I'm just going to put that glue, the same thing. GABA, GABA, glue. Now, all neurons are spontaneously active unless they're inhibited. So, if this GABAergic neuron fires, what happens to this GABAergic neuron? Doesn't fire. This one does what? Does fires. This is disinhibition. Disinhibition. Okay? Let's put let's put GABA, 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 glue. Okay? If this GABAergic neuron fires, what happens to this GABAergic neuron? Doesn't fire. Which happens to this one? Fires. What happens to this? Doesn't fire. Okay. Here's how it works out. Whenever you have an even number of GABA neurons, you get disinhibition. Excuse me.
No.
Whenever, excuse me.
Opposite.
No. Let me think about this again. Because I'm screwing myself up. Glue, okay. GABA, GABA, glue, okay, you get disinhibition, so it fires. So that's an even number of GABAergic neurons. Okay? 1, 2.
Yes.
GABA hits GABA, which means this fires.
Mm-hmm.
If we have 1, 2, 3, what happens? Inhibition. So if you have an odd number, you'll find out you get inhibition. Even number, okay, disinhibition. Okay, odd number, inhibition. You can try that for 5, 6, whatever you want. Every time you have an even number, you're going to get inhibition. Here we go. Every time you have an even number, you get disinhibition. Every time an odd number of glutamate neurons, okay. You say glutamate, GABA neurons, okay, you get inhibition. All right. Now, let's make an analogy. Supposing you turn your car on, okay, so you've already turned the ignition, it's on. To make your car move, you have to do 2 things. What are the 2 things that are required to make a car move? Forget about putting it.
Drive.
Yeah, it's not that.
Yes.
Okay? You have to put on the gas. Okay? There's also something else you have to do.
Start the engine.
I already started it.
Put in drive.
Let go of the brake. Take the brake off.
Oh.
So,
True.
what you can think about in this system is there's one major pathway that acts as, before dopamine gets there, that acts as the gas. Okay? That acts as the gas. There are other pathways that act as brakes to movement. We want to decrease the braking ones. We want to increase the ones that are the gas. Now, I'm going to show you in this picture. We're going to start from the striatum. We're going to start from the striatum. Okay? And what we're going to do is, supposing we activate this neuron, this is called the direct pathway. See the one going right down the middle? So you have the dark black arrows, the one going down the middle. That's called the direct pathway. Okay? Now, look at the system from here. GABA, GABA, glue. Wouldn't we say whenever you have an even number, what was that going to lead to?